It will be an incredibly exciting future where we're a spacefaring civilization, people on every part of our solar system, and eventually going to other star systems.
SpaceX is preparing Flight 14 to place useful payloads into orbit and potentially return Starship to the launch tower for the first ever ship catch. A real orbital mission changes the return timeline because Starship cannot simply just turn around and fly back to Texas whenever SpaceX wants it to. The ship may have to circle Earth for hours while Starbase rotates back into the right position beneath its orbital path. Could that unavoidable wait become a full-scale rehearsal for the long-duration propellant mission expected to follow on Flight 15? That possibility connects Flight 14 directly to one of the hardest jobs Starship has ever been built to perform. SpaceX's published refueling sequence begins with one Starship spending an extended period in orbit, preserving its liquid methane and liquid oxygen until a second ship launches, rendezvous, docks, and transfers propellant. Now, Flight 14 could test nearly every part of that waiting period without placing a second vehicle at risk. We're going to break down the orbital mechanics, cryogenic boil-off, propellant settling, engine restart, power, docking hardware, and why SpaceX may need this data before Flight 15. What SpaceX has announced is an attempt to send operational payloads to orbit, followed by a possible ship catch if the vehicle and regulatory approvals are ready. Put those goals beside SpaceX's published transfer plan, and several hours in orbit become technically useful rather than empty, waiting, wasted time. The first reason is orbital geometry. A Starship flying in low Earth orbit may complete one revolution in roughly 90 minutes. But Earth rotates beneath that orbit by about 22 degrees during that same period. Now that means the spacecraft's next ground track does not pass over the same points it crossed on the previous lap. To return to Starbase, the ship needs an orbit, deorbit burn, entry corridor, and arrival time that bring it back to the narrow path of South Texas with the correct direction and energy. SpaceX can shape the initial orbit to create a planned return opportunity, but it cannot ignore the movement of Earth. Depending on the exact inclination, altitude, insertion point, and recovery corridor, the right pass may arrive many orbits after launch, and the wait could last several hours and perhaps a large part of a day. The booster would be back near the tower within minutes, while the ship continues circling at close to orbital velocity. That creates a rare opportunity. Flight 14 can act like the waiting ship in a propellant transfer mission, except there would be no tanker approaching it yet. SpaceX can watch how the complete vehicle behaves through multiple sunrises, sunsets, and attitude changes, communications handovers, and propellant settling maneuvers. And if a valve drifts, a tank warms too quickly, a battery runs low, or a navigation sensor disagrees with the others, engineers can find the problem before two starships are ever docked together. Now, the cryogenic propellant is the center of this test. Starship burns liquid oxygen and liquid methane, which have boiling points near minus 183 and minus 162 degrees Celsius at normal atmospheric pressure. The actual temperatures inside Starship depend on tank pressure and operating conditions, but both liquids remain extremely cold. Heat entering through the steel walls, plumbing valves, and structural connections can boil some of that liquid into gas. Boil-off creates two connected problems. Gas raises pressure inside the tank, and the vehicle may eventually have to vent some of it to stay within safe limits. Every kilogram released through a vent is propellant that can no longer be transferred or burned. A tanker architecture only works if Starship can hold large quantities of methane and oxygen long enough for the next launch to arrive. Flight 14 would give SpaceX a clean measurement at that loss rate on the new version 3 ship. Engineers can compare tank pressure, wall temperature, vent activity, vehicle attitude, and repeated passages between sunlight and Earth shadow with the amount of usable liquid remaining. A 1-hour flight provides a snapshot, while a multi-orbit mission begins to show a trend. That trend helps SpaceX estimate how much margin Flight 15 would need if it waits in orbit for days rather than hours. Version 3 was redesigned for this exact class of mission. SpaceX says the ship uses vacuum-jacketed headed tank feed lines, electrically operated cryogenic recirculation, isolation valves for high-pressure gases, and a dedicated system that manages interactions between the engines and cryogenic propellant during extended coasts. Those systems sound like plumbing details, but they decide whether a Raptor engine receives dense liquid or a dangerous mixture of liquid and gas after hours in space. Flight 14 could place all of them in a real thermal environment before Flight 15 depends on them. Microgravity makes the problem far stranger than ordinary fuel storage. On the ground, gravity gives every tank a clear top and bottom, and the liquid collects over the outlet. In orbit, methane and oxygen can spread along the walls, form large floating masses, trap gas near an outlet, and begin sloshing when Starship rotates. A conventional level sensor can struggle because there may not be flat liquid surfaces to measure. Now, SpaceX has developed radio frequency propellant gauges for that job. These sensors use the electrical properties of the material inside the tank to estimate how much liquid is present, even when it's distributed unevenly. During Flight 14, engineers could compare the gauge readings with every thruster firing, vent, roll maneuver, and engine operation. Reliable gauging is essential because the transfer system must know how much propellant left one ship, how much reached the other, and whether either vehicle still has enough for its own return. The liquid also has to be settled before it can move through the plumbing cleanly. Small thrusters can give the ship a gentle acceleration that pushes propellant toward the desired end of the tank. The maneuver must be strong and long enough to collect the liquid while avoiding violent slosh that wastes settling time or destabilizes the vehicle. Flight 3 already moved thousands of pounds of liquid oxygen between tanks inside one Starship, and NASA studied the resulting slosh stability, transfer efficiency, and conditions needed for Raptor restart. Flight 14 can extend that lesson across many more orbits. SpaceX could command repeated settling maneuvers, observe how quickly the liquid calms down, and see how much reaction control propellant those maneuvers consume. It could then allow the tanks to coast again and watch the liquid redistribute. That cycle would help engineers tune the procedures that Flight 15 may use before receiving propellant from another ship. Flight 14 may tell us far more about orbital refueling than the official objective list suggests. The data after launch will be just as important as the catch attempt. And the delayed deorbit burn could be the most important single event of that flight. A Raptor vacuum engine that restarts after several hours must receive settled propellant at the correct pressure and temperature, while valves, igniters, turbopumps, avionics, and electrical systems all wake up in the right sequence. SpaceX demonstrated an in-space Raptor relay on Flight 6, but a much longer coast places more stress on the thermal and propellant management system. And if Flight 14 performs a clean burn after many orbits, it proves that the ship can wait and still control its own fate. The receiving Starship may need to perform phasing burns, attitude corrections, collision avoidance maneuvers, and eventually a deorbit or departure burn after waiting for the tanker. And the tanker must complete its own burns to enter the correct orbital plane, adjust its positioning along that orbit, and approach at a controlled closing rate. Engines that work only shortly after launch would make the entire plan completely impossible. Flight 15 would add the next layer, finding it approaching another 9-meter wide Starship. SpaceX plans to use Dragon Eye sensors derived from Dragon rendezvous operations, plus docking ports and propellant connections built into version 3. The ships must measure relative range, orientation, and closing speed with extreme precision, while both travel around Earth at roughly 28,000 kilometers per hour. They then have to make physical contact without damaging the ports, seals, flaps, or heat shield areas nearby. Now, this is why SpaceX would use Flight 14 as a pathfinder instead of saving every new objective for Flight 15. A 2-ship test already combines 2 launches: precise orbital insertion, phasing, rendezvous, docking, fluid transfer, separation, and recovery. Adding the first extended coast to the same mission would make fault diagnosis much harder. If the waiting ship loses propellant too quickly, engineers need to know whether the cause was its thermal system, its attitude plan, a transfer line leak, or an interaction with the tanker. And there's still a major limit to what Flight 14 could prove. Hours in orbit do not certify a ship to wait several days for a tanker, and one successful restart does not guarantee repeated burns throughout a full transfer campaign. Boiloff rates can change as tanks empty, surfaces warm, and orbital lighting conditions shift. And Flight 14 would provide the first part of the curve, while Flight 15 may have to extend that curve long enough to meet the second vehicle. Now, the reason for taking the risk reaches far beyond 2 test flights. A lunar Starship cannot launch from Earth with enough propellant to land on the moon and complete its mission. So SpaceX's architecture depends on refilling it in orbit. That may require a receiver or depot to wait while several tanker starships launch one after another. Mars missions demand the same basic abilities on longer timescales. Store cryogenic propellant, know where it is inside the tanks, restart engines after coasting, and move fuel between vehicles without losing control. Flight 14 may look like a payload mission followed by a spectacular catch attempt. The hours between launch and return could carry the more important technical work, though. Every orbit can test whether Starship remains cold, powered, stable, measurable, and ready to restart. And if those systems hold together, Flight 15 can move from simply surviving in orbit toward meeting another Starship and transferring the propellant that makes the entire Moon and Mars architecture possible.